This video will cover volumetric analysis. By the end of this video, you should understand the concept of volumetric analysis, be able to use titration vocabulary correctly, and be able to perform titration calculations. Volumetric analysis is an analysis method that uses titration to determine the amount of a given substance present. As the name implies, it's based on volume and concentration. A titration is a process by which we deliver a solution of a known concentration into a solution of an unknown concentration. Since we know the concentration and the amount of the known solution it takes to completely react with the unknown solution, we can use this to calculate the concentration of the unknown solution. Titrations are most commonly used for acids and bases, but this is not the only way in which titrations can be used. They're often used as an analysis method for many other types of reactions. Let's start with some titration vocabulary. Since titrations are most often used for acids and bases, we'll talk about this vocabulary in terms of acids and bases, but do bear in mind that titrations can be used for other types of reactions as well. First, we have the equivalence point. The equivalence point is the point in the titration where the moles of acid are stoichiometrically equal to the moles of base. This is often marked by an indicator, which changes color. The end point of a titration is the point where the indicator actually changes color. Since indicators usually change color once the amount of acid or base has been exceeded, this will happen just slightly after the actual equivalence point. Ideally, we use an indicator that changes color exactly or as close as possible to the equivalence point. This will signal the end of our titration. Some more titration lingo. First, we have the titrant. This is the solution of known concentration. It's often also known as the standard. Usually this will go in the burette for a titration. Then we have the analyte. The analyte is the solution of unknown concentration. As the name implies, this is the solution we're analyzing to determine the concentration. As we mentioned before, the goal of a titration is to determine how many moles of solute are in the unknown solution. We can use volumes to convert between moles and concentrations. Here's a schematic of a common acid-base titration. In this diagram, NaOH, which is our solution of known concentration, is placed in the burette at the top. This solution is known as our titrant or standard. It will then be slowly added in small increments to our solution of unknown concentration, in this case HCl. This is known as our analyte. We'll add NaOH to HCl until all of the HCl has reacted and there's no more in the solution. From here, we can determine how many moles of NaOH we added, and we know that at the equivalence point of the titration, the moles of NaOH will be equal to the moles of HCl, allowing us to determine the original concentration of the HCl. Looking at the steps involved in a calculation for a titration, first we start with the volume of the standard solution needed to reach the equivalence point. Using the molarity of this solution and the volume we used, we can calculate the moles of solute that we used from the standard solution. Then, using the mole ratio from our balanced equation, we can calculate the moles of solute in our unknown solution from the moles of solute we used from the standard solution. And finally, we can use our molarity equation again with our moles of solute and our volume of solution to calculate the concentration or the molarity of the unknown solution. Let's look at an example problem together. Here we're told that a 25 milliliter sample of unknown HCl is titrated using a 0.75 molar solution of NaOH. The endpoint occurs at 34.5 milliliters. We're asked to calculate the concentration of the unknown HCl. First, let's consider what's what here. Since we're told that we have a 0.75 molar solution of NaOH, we know that NaOH must be our standard or our titrant or our solution of known concentration. We also know that the endpoint occurs at 34.5 milliliters, meaning it took 34.5 milliliters of NaOH to completely react with the HCl. The HCl, on the other hand, is our unknown because we don't know the concentration. Let's follow the steps laid out previously. First, we'll write a balanced equation. Here, 1 mole of NaOH reacts with 1 mole of HCl to produce 1 mole of NaCl and 1 mole of water. Then, we'll determine the moles of titrant used. Using the molarity equation, molarity equals moles over liters, we can plug in the values we know. Here we know that we had 0.75 molar NaOH, and we used 0.0345 liters. Always remember to convert to liters when using the molarity equation. Solving for moles, we get 0.026 moles of NaOH. That means we used 0.026 moles of NaOH to react with all of the HCl in the unknown solution. Now we can use the mole ratio to determine how many moles of HCl were present. Since our balanced equation tells us that for every 1 mole of NaOH we have 1 mole of HCl, we know that our moles must be equal, giving us 0.026 moles of HCl present in the original solution. Finally, we can use this value and our volume to calculate the molarity of our HCl. Again, we plug in our moles of HCl and our liters of HCl, 0.025. Solving for x, we find that the concentration of our HCl was 1.0 molar. Here's an example to try on your own. You'll notice that this example is not an acid-base titration. It's a different type of titration, but the process remains the same. Pause the video here and follow the steps laid out. When you return, I'll reveal the answer. Welcome back. Here's what you should have gotten. That brings us to the end of the volumetric analysis video. Let's review our goals. First, we looked at the concept of volumetric analysis. Then, we introduced some titration vocabulary. And finally, we practiced performing titration calculations.